Welcome back everyone. In this lecture we will continue with the representation theory of finite groups. So, let us fix some notations as before. So, we fix G to be a finite group. So, we talked about equivalence of representations. In particularly we defined homomorphism between representations. So, let us actually try to understand what happens with equivalent representations. So, let us say we have v comma rho and then w comma xi. So, these are the given G representations. So, that means you have rho which is a map from G to GL of V, and then you have xi which is again a map from G to GL of W. So, let us say we have this homomorphism or interturning operator. So, let us call it T from V to W. So, this is the homomorphism. So, in particularly we have the following diagram. So, we have this map. So, given G in G, we can talk about this rho of G, and then we have this map T, and then we have this xi of G here. And so, this is a homomorphism is equivalent to saying that this diagram actually commutes. So, that means you first apply rho G and then T. So, that is same as saying that you apply xi of G and T, and this is true for all G and G. So, this is what we expect, and one can easily check. So, I will leave it as an exercise. The homomorphism between these G representations will be equivalent to homomorphism of CG representations. So, that is not hard to prove. So, now once you have this intertwining operator, as before one can define the kernel and then image. So, these are all again representations of G. So, this is easy to see, and they becomes sub representations. Okay. So, this is a sub representation of V and this is a sub representation of W. And not only that, using these representations we will be able to actually define the quotient, and then we can see the first isomorphism theorem. So, V modulo the kernel will be naturally isomorphic to the image of T. So, this is the isomorphism as G representation. So, for example, let us recall how one defines this quotient. So, if we take this quotient V modulo the kernel. So, if I take some V here, so which is the V bar, so which looks like V plus the kernel T, and then given element G in G, you want to define this induced representation. So, let us call it rho tilde from G to GL of V modulo the kernel T. So, this you define as follows: rho tilde of G on this V plus kernel T, you define it to be rho G of V. Plus kernel T. Since kernel T is already invariant under the action of elements of G, and rho of G is a map from V to V. So, rho of G induces a map from V modulo kernel to V modulo kernel. So, that is the map that we are actually defining here. And so, one wants to check this is indeed gives us representation, because we want rho tilde to be group homomorphism. So, first of all, rho tilde of G must be invertible element, that is the important thing to check. So, what is rho tilde of G? Basically, this is an induced map that is coming from rho G. So, we need to prove this is indeed invertible. So, recall rho of G is a map from V to V, and rho of G leaves the kernel invariant. So, that is how you are getting this rho tilde of G, which is a map from V modulo the kernel T to V modulo the kernel T. So, now if you think about it, because the both side we have same spaces, if we prove that rho tilde of G is indeed injective, it is enough to say that this is indeed invertible map. So, let us look at what happens when we have the element in the kernel. So, then the V plus let us say kernel T is killed by the action of rho tilde of G. So, then that means that rho of G, because the map that we have defined, that is actually rho G V plus the kernel T. So, that means this is exactly rho G V belongs to the kernel T. Okay, but then you can see that so we want to say that V itself there in the kernel T. So, if we are looking at this TV, so we want to prove, so this is the claim that TV is indeed 0. So, that is V itself in kernel T. Okay, so how do we check this? So, we can actually check that T of rho G V is indeed 0. Okay. So, that means we get xi G T V is 0. So, now if we go back T being the intertwining operator, you can see that T rho G is same as xi G T. So, that means we get these two things are equal. T rho G V is same as xi G T V, but since xi G is invertible, that would imply that the kernel of xi G is 0, and that would imply that T V is 0. So, this is what we required actually. So, that means this map that we got is indeed invertible map. So, that is actually good enough to prove, because rho tilde is induced from rho. So, since rho is group homomorphism from G to GLV, so that would imply that rho tilde is a group homomorphism from G to GL of V modulo kernel T. So, this is something one can do it for any invariant subspace. Maybe I will leave it as exercise. So, suppose U is subrepresentations of V. So, then you can actually make this this U modulo V modulo U as a representation of G. The action is defined to be take V comma rho to be the representation. So, then this rho tilde of G of V plus U is defined to be rho G of V plus U. So, this is how the action is defined. The action defined as follows. Okay, so and one can check that rho tilde of G is indeed rho tilde is indeed a representation, and that is called actually quotient representation. And if you go back to the definition of quotient representation that we introduced for associative algebras, then you can easily see that this actually matches with that. Okay, so if we are actually working with the equivalent representations and it is not hard to actually translate some of the information that we know about one representation to another representation. So, what I mean by that, so we have the following exercise. So, let us assume that given two representations are isomorphic or equivalent representations. So, then it is easy to prove that if V is irreducible, that would imply that W is irreducible. Indeed, what one can show, if U is subrepresentation of V and pi is the isomorphism between V and W. So, if this is G subrepresentation, so then you can easily see that pi of U is going to be a subrepresentation of W. And similarly, like all other terminologies like completely reducible, decomposable, everything actually translates to the other representation. If V is completely reducible, then so is W. And like I said, you can replace this by indecomposable, decomposable, and so on. For example, if you have a filtration for V, then we can pull back that and then get filtration for W. So, so its equivalent representation will actually possess same information. So, let us see one example of equivalent representations. So, I am going to define indeed two dimensional representation of cyclic group. So, let us take G to be the finite cyclic group Z modulo n Z, and then I want to actually define two dimensional representation C2. So, for that what we do, we simply actually take this phi. We want to define this group homomorphism from G modulo NZ to GL2 of C. So, now the elements of this group, let us say they are all denoted by these classes M, where M is varying from 0 to n minus 1. So, now given this M, we just simply map this M modulo class n. So, this is mapped to, let us say, this 2 by 2 matrix, which is given by cosine 2 by m n minus sine 2 by m by n. Similarly, here sine 2 by m by n and then plus cosine 2 by m by n. So, now if you think about it, this indeed defines a representation. So, the action of the group element is indeed given by the rotation by 2 pi by 2 pi m by n. So, this is actually indeed corresponds to the rotation by 2 pi m by n. So, now basically what we have done, we have used the basis 1 comma I. So, basically 1 comma I. So, this is the basis that we have used of C 2 over C. So, then we have written indeed this 2 e power 2 pi m I by n as cosine 2 pi m by n plus I sin 2 pi m by n. Okay. Similarly, if you think about it, the other coordinates corresponds to e power minus 2 pi m I divided by n. So, in this representation, so this is the matrix for the rotation by 2 pi m by n. So, now we can actually define another representation xi, which is again a map from z modulo n z to gl to c. So, which is given by, so the class m maps to this e power 2 pi m I divided by n 0 0 e power minus 2 pi m divided by n. So, now it is not hard to see this phi that we defined before is indeed equivalent to the xi, and the intertwiner matrix actually given by the following map, which is the T. So, which is given by I minus I 1 comma 1. So, one can use this T and then easily check that T inverse phi m T is going to be exactly equal to xi of m. So, this is something I will leave it to you to check. So, this is just a matrix computation. So, basically we are looking at two different bases of C 2 over C, and then the change of basis is recorded in this matrix T. Okay, so, this explains the equivalent representations. So, let me actually give some examples of representations. So, let us see first of all some one dimensional representations. So, we have already seen one trivial representation. So, now for example, like if you are working with a cyclic group, what we can do, we can simply define the following one dimensional representation. So, we can simply take phi to be a map from G modulo n z G to C star, which is given by the mth class is mapped to e power 2 pi I m by n. So, we will see later that any finite dimensional representation of this G modulo n z will be indeed decomposed as direct sum of one dimensional irreducible representation. So, here one can easily prove that since this representation is one dimensional. So, this must be irreducible, and similar to this, like one will be able to define for any k representation of z modulo n z. So, all we need to do is simply take instead of e power 2 pi m by n, we can just simply multiply by k with that. So, the image of this is given by e power 2 pi I Km divided by n. So, basically the generator 1 is mapped to this e power 2 pi I k divided by n, and then the group homomorphism is determined by using this map. Okay, and I will leave it as exercise. This is indeed gives us one dimensional representation, and this is also irreducible. And later we will actually prove that. So, we can take this k to be between 0 and n minus 1. So, we will prove that these are all the only irreducible representations of actually z modulo n z, and all other finite dimensional representations, they will be actually direct sum of these irreducible representation, one dimensional representations. Okay, so now we will actually use little bit of group actions in order to define some new representations. For example, we can use the standard action of a symmetric group on Cn by permuting the coordinates to obtain the standard representation of Sn. So, here is the standard representation of Sn. So, to define this, we need to define the group homomorphism. We have to say that how Sn acts on the given vector space. So, the standard representation, the degree will be n. So, we simply take this GLN of C. So, and then we fix this EI to be the standard basis, E1 etc. En to be the standard basis of Cn. So, now given sigma, so we define the action of sigma by permuting the coordinates. So, that means by permuting the standard basis. So, given sigma, the phi standard sigma is defined to be a map from Cn to Cn, and which is a linear map. So, it is enough to define it on the basis. So, that is defined to be of Ei is send it to E sigma I for all I1 to n. And it is not hard to check, this is indeed gives us a group homomorphism from Sn to JLN C. And if we use the standard basis and then write down the matrix of each map phi standard sigma. So, we can easily see that it exactly permutes the columns of the identity matrix. So, let us actually just work out some example. So, let us take n to be 3, and then if we take sigma to be the transposition 1 2, then we can easily see that E1 is mapped to E2 and then E2 is mapped to E1. So, that means the matrix of sigma with respect to B. So, that is exactly going to be just because E1 is mapped to E2 and then E3 is mapped to E3. So, this is going to be 0 1 0 and then 1 0 0 and then 0 0 1. So, that means we have taken this identity matrix which is 1 0 0 0 1 0 0 0 1, and then we just apply sigma on the columns of this identity matrix. So, this first column move to the second column and then second column move to the first column under the sigma. So, the resulting matrix is just 0 1 0 1 0 0 0 0 1, which is exactly obtained by applying phi standard sigma. So, this is how all these permutation matrices are obtained. So, basically if we look at this phi standard sigma and then the matrices of that with respect to the standard basis, this is going to be the permutation matrix corresponding to sigma. So, what it is exactly you obtain you start with the identity matrix and then permute the columns according to the sigma. So, let us say this is the identity matrix E1 etc. En, then from here you get this permutation matrix corresponding to sigma as E sigma 1 etc. E sigma n. So, this is how you get the corresponding matrix. So, now note that if we take this sum of these all basis elements, then if I apply sigma on this, so then we will get back this sum of these EIs. So, because sigma is just going to permute 1 to n. So, this quantity is going to be exactly equal to E sigma 1 plus etc. plus E sigma n, but sigma just permutes 1 to n. So, by rearranging we get exactly E 1 plus etc. E n. So, that means this subspace spanned by this E 1 plus etc. E n. So, this is indeed Sn invariant subspace. So, this is indeed sub representation of this Cn, standard representation Cn. So, if we take the orthogonal complement of this, let us call it capital V. So, this is going to be those vector in Cn that is exactly orthogonal to this E1 plus etc. plus En. And one can easily see that this is also a sub representation. So, this is also a sub representation of Cn. So, that is because, so when we do this sigma, so the inner product, standard inner product becomes invariant under this. So, note that if we apply sigma V, so if we start with V in V and then if I compute sigma V on this E1 plus etc. plus En, so this is going to be exactly equal to V sigma inverse of E1 plus etc. plus En. But since this E1 plus etc. En is sigma invariant or entire G invariant, so this is exactly going to be equal to V comma E1 plus etc. plus En. So, which is exactly 0. So, that means the sigma V again lies inside this subspace V. This is indeed a sub representation. But if we just work it out and then we can easily see that this EI minus EJ, so these elements all will lie inside capital V and then we can easily find the basis E1 minus E2, E2 minus E3 etc. En minus 1 minus En. So, this is maybe we can call it as alpha 1 etc. alpha n minus 1. This form a basis of this capital V. So, in particularly the standard representation is indeed decomposed as this V direct sum, this one dimensional indeed trivial representation, because sigma on this E1 plus etc. plus En gives us E1 plus etc. plus En. So, that means this space that we are getting here, so this is indeed a trivial representation or isomorphic to trivial representation, and this is indeed sub representation. So, one will be able to actually prove this is indeed irreducible Sn representation. So, this V, which is the span of this Cn, so this is exactly equal to V comma E1 plus etc. plus En. So, this is indeed E1 minus E2 etc. En minus 1 minus En. So, this is indeed irreducible subrepresentation of Cn standard. Maybe I will leave this as exercise. Okay, I will stop here. We will continue with the representation theory in the next class. Thank you.